Lesson planning in mathematics often breaks down at the very beginning. Teachers are told to plan from standards, but what that actually looks like in daily math instruction is rarely made explicit. For many, curriculum providers have always aligned to the standard as an afterthought. As a result, planning often starts with a worksheet, a set of practice problems, or a digital activity, and the standard is added afterward. That approach may match the topic, but it does not guarantee that students are developing mathematical understanding. Math standards are not lists of procedures. Planning from standards in math means designing or adapting lessons where students reason, model, justify, and connect representations, not just calculate correctly. The standard names the mathematical goal. The lesson must create opportunities to practice the mathematics behind that goal. To make this manageable, teachers need a repeatable planning method that works across topics. This is not about writing longer lesson plans. It is about making a small number of high-leverage decisions that shape tasks, questions, representations, and assessments. The first step is to unpack the math standard before choosing any activity. Read the language carefully and scan for verbs and nouns. Verbs tell you what mathematical actions students must take, such as represent, interpret, justify, compare, or model. Nouns tell you the mathematical objects students must reason about, such as proportional relationships, slope, functions, or area. From these, name two things clearly. The concept is the mathematical idea. The reasoning is how students must think with that idea. This step matters in math because it prevents a common instructional error. Teachers often teach procedures tied to the concept, but remove the reasoning the standard requires. Naming both the concept and the reasoning keeps the lesson focused on mathematical sense, making rather than step following. Next, translate the standard into a four-part planning map. First, identify what students must know. This includes vocabulary, definitions, units, and core ideas. Second, identify what students must do. This includes creating representations, solving contextual problems, and explaining reasoning. Third, identify what students must decide independently. These are the mathematical choices students must make without being told what to do. Fourth, identify what counts as evidence of understanding. This is what you would accept as proof that the student understands the mathematics, not just that they got an answer. To see how this works in math, consider a middle grade standard focused on proportional relationships. The standard asks students to recognize and represent proportional relationships, and use them to solve problems. Using a planning map, what students must know includes ratio language, unit rate, multiplicative comparison, and the meaning of a constant of proportionality. What students must do includes analyzing situations, creating or interpreting tables, graphs, and equations, and explaining how those representations relate. What students must decide independently includes whether a relationship is proportional, which quantities are related, which representation to use, and how to justify that choice. Evidence of understanding includes explaining why a situation is proportional, interpreting the unit rate in context, and connecting multiple representations consistently. Now plan representations explicitly. In mathematics, representations are not just tools, they are the mathematics. For proportional relationships, the representations include ratio tables, graphs that pass through the origin, equations of the form y equals kx, and written explanations with units. Planning must include moments where students move between at least two representations and explain how they correspond. If students never connect representations, understanding remains fragmented. Next, anticipate common mathematical misconceptions. These are predictable and valuable. In proportional reasoning, students often use additive reasoning instead of multiplicative reasoning, assume any straight line represents a proportional relationship, or treat unit rate as a procedure without meaning. Planning for these misconceptions allows you to design questions and comparison moments that surface reasoning instead of correcting it immediately. Before selecting a task, write student-facing success criteria that reflect mathematical reasoning. These describe what it means to understand, not just to finish. For example, I can explain how I know a situation is proportional using multiplicative reasoning. I can choose a table, graph, or equation and justify why it represents the situation. I can explain what the unit rate means using correct units. These criteria help students attend to precision and meaning. Only after this analysis do you select or design the task. A low-demand math task might provide an equation, tell students what to graph, and ask them to calculate values. This aligns by topic but removes mathematical decision-making. A high-demand math task presents a context, asks students to determine whether the relationship is proportional, choose a representation, and justify their reasoning using units and structure. The numbers may be similar, but the mathematics is very different. Planning also includes teacher moves that preserve mathematical thinking. Instead of planning explanations, plan questions. Questions like which quantities are changing together? How do you know the relationship is multiplicative? Why must this graph pass through the origin? What do the units tell you? And convince me this representation fits the situation. Keep the math work with students. These are core math teaching moves. Plan scaffolds that change access to the mathematics, not the mathematics itself. In math, good scaffolds preserve structure. Examples include using friendlier numbers that keep the same relationships, offering partially completed representations without showing the solution path, providing representation menus rather than assigning one, and offering sentence frames that support justification without telling students what to say. Plan math-specific formative checks aligned to the success criteria. One check might present a new situation and ask students to decide proportional or not, and explain why without calculating. Another might show an incorrect graph or table and ask students to analyze the error and explain what does not match the situation. Error analysis is especially powerful in math because it reveals reasoning. This planning process produces concrete math teacher artifacts. A one-page standards to lesson planning map. A set of student-facing success criteria focused on reasoning and precision. Task analysis notes identifying mathematical decision points. Planned questions that press for justification and connections. A differentiation plan that preserves the same mathematical goal. Informative assessment prompts that surface understanding, not just answers. This approach is grounded in math education theory. Backward design explains starting with evidence of mathematical understanding. Cognitive load theory supports using clear representations and structured planning to reduce distraction while maintaining reasoning demand. The zone of proximal development explains why productive struggle is essential in math learning and why scaffolds must be temporary. Universal design for learning supports planning multiple representations and ways to show mathematical understanding. Self-determination theory explains why autonomy in representation choice, clear expectations, and respectful math discourse increase persistence in challenging problem-solving. Technology can support math planning and instruction when used intentionally. Digital math tools allow students to test representations, visualize relationships, and compare strategies without lowering rigor. AI can support planning by generating possible misconceptions, draft success criteria, sample high-demand task contexts, or error analysis examples for a given math standard. Teachers then evaluate those ideas using the planning map to ensure the mathematics stays intact. When math lessons are planned this way, standards stop feeling abstract. Planning becomes about designing opportunities for students to think mathematically. The guiding question remains consistent across topics and grade levels. What mathematical thinking does the standard require, and how will this lesson give students practice doing that thinking independently?